Welcome to GATE CSE. We'll solve some problems on eigenvalues and eigenvectors and diagonalization of the matrix. Given this matrix, determine the eigenvalues of it. So if you observe here, see there are zeros in the lower part. This is an upper triangular matrix. So the eigenvalues will be its diagonal elements. So the eigenvalues will get lambda 1 equal to 3, lambda 2 equal to 4, lambda 3 equal to 4. Find the eigenvalues of this matrix. So please check, is it a diagonal matrix or triangular matrix? No. So then we'll go for our normal approach. 2 minus lambda 0 0 minus 1 2 minus lambda minus 1 0 minus 1 then 2 minus lambda equal to 0. Find the determinant 2 minus lambda into 2 minus lambda into 2 minus lambda plus 1 minus 1 is equal to 0. So equate this. So lambda will be equal to 2. Then 2 minus lambda whole square is equal to 1. So 2 minus lambda is equal to plus or minus 1. So lambda equal to, will get 1, 3. So 1, 2, 3 are the eigenvalues of this matrix. Next, determine an eigenvector of this matrix corresponding to eigenvalue lambda equal to 3. So it's a diagonal matrix because only diagonal elements are present. So for 2, 3, 4 are the 3 eigenvalues I get. So for lambda equal to 3, you find the eigenvectors. How will you find eigenvectors? So this is a minus lambda I, that is 2 minus lambda 0 0 0 3 minus lambda 0 0 0 4 minus lambda. So lambda is equal to 3. Substitute that value. So this becomes minus 1 0 0 0 0 and 0 0 0 1. This is applied to a vector, say x1 x2 x3 equal to 0. Then find this vector now. So this will be minus x1 is equal to 0. Then x2 is not there. Then x3 is equal to 0. So this is set. Now I can take x2 can be some value, say 1 into t, or it can be 0 into t. Why, I will tell you. Now what are the possible vectors now? So this vector will be p is equal to t into x1 is 0, x3 is 0, x2 can be t into 1, that is 1 into t. Now this is one of the eigenvector. Should also check for the other combination 0 into t. What I will get if I get p equal to t into 0 0 0. So all zeros, this is not a eigenvector. Please remember this point. This is not a eigenvector. If I get all zeros, zero vector is not a eigenvector. Cannot consider this. So this is the answer. Okay. Next, find the eigenvector corresponding to lambda equal to 5. This is an upper triangular matrix. Okay. So 1, 3 and 5 are my eigenvalues. So for lambda equal to 5, you calculate the eigenvector. So it will be 1 minus 5, 2, 1, and then 0, 3 minus 5, 4, 0, 0, 0. So this will be equal to minus 4, 2, 1, 0, minus 2, 4, 0, 0, 0, and then my eigenvector, that is x1, x2, x3 will be equal to 0. So this is 4x1 plus 2x2 plus x3 is equal to 0, the first row. Then second is minus 2x2 plus 4x3 is equal to 0. So I can write it as x2 is equal to 2 x3. Then the last one, the free variables. So let me put x3 is equal to 1 into t or 0 into t. Will check both. Now, when x3 equal to 1 into t, what I will get? x2 will be 2 into t, or when it is 0, it will be 0. Now, what will be x1? x1 will be 1 equal to, so this is 2x2 plus x3. So x1 is 2x2 means 2x3, that is 4x3 plus x3. So x1 equal to 5x3. What is x3? T. Okay. So this is nothing but 4x1, right? So divided by 4. Or if I put 0, it will be 0. Now, what are the eigenvectors? Eigenvectors will be t into, so x1 is 5 by 4, x2 is 0, x3 is 0. Okay. Find an eigenvector for this lambda equal to 5. That means it's a super triangular matrix. So eigenvalues will be 1, 3 and 5. Now for corresponding to eigenvalue 5. So let us, so 1 minus 5 is minus 4, 2, 1, 0, minus 2, 4, 0, 0, 0. Then my vector x1, 2, x3 is equal to 0. So this is 4x1 plus 2x2 plus x3 is equal to 0. Then minus 2x2 plus 4x3 is equal to 0. This implies 2 is equal to 2x3. Then the last one is not there. Okay. So x1, x2, x3. So none of the variables are free variables here. So that means what? All are linearly independent. That is the meaning. So now we'll see. Let us put x3 is equal to t. Then x2 will be 2t. Okay. So now you put 4x1 minus 4x1 is equal to minus 2x2 minus x3. So x1 is equal to 2x2 plus x3 by divided by 4. So x1 will be 2x2, x2 is 2t. So 4t plus x3 is t divided by 4. So x1 is equal to 5 by 4 t. So what are my eigenvectors? P is equal to t into, so x1 is 5 by 4, and then you have x2 is 2t, and then here you have t 1. So you can convert it into integer for convenience. T into becomes 5, you multiply by 4, 8, and then 4. This is the answer. Okay. Let A be a 3 cross 3 matrix with eigenvalues 1, 2, 3. Then find the determinant of A square plus I. You already know determinant of A power k is equal to lambda 1 power k into lambda 2 power k and so on, where lambda 1 and lambda 2 are the eigenvalues of matrix A. Okay, so now they are asking A square plus I. So how it will write? Determinant of A square plus I. I is the identity matrix. This will be equal to lambda 1 power 2 plus eigenvalue of a identity matrix is 1 into lambda 2 square plus 1 into lambda 3 square plus 1. Okay. For any identity matrix, 1 is the eigenvalue. So this will be 1 plus 1 into 4 plus 1 into 9 plus 1. This will be 100. There are no options here. The answer is 100. Next. If A is invertible and has eigenvalue lambda not equal to 0, the corresponding eigenvalue of A inverse. So if a given matrix A and the eigenvalue is not 0, then it means what? A is invertible. That means I can find the inverse of A. So what will be the inverse of? What will be the eigenvalue for the inverse of A? That will be 1 by lambda. Next. Let A be 3 cross 3 matrix with eigenvalues 1, 2, 3. Which of the following statements are true? Now, trace of a matrix is given by the product of its or sum of its eigenvalues, that is 1 plus 2 plus 3, that is 6. This is correct. Then determinant is given by product of that eigenvalues. So this is 6, that is also true. Now, eigenvalues of A square are, so it will be a lambda power k, or that is lambda square here. So 1 square plus 2 square plus 3 square, this is also true. Then eigenvalue of A inverse are, so 0 is not here, eigenvalue 0 is not there, so you can get the inverse as 1 by lambda. So all the 4 statements are true. Next, if A and B are similar matrices means what? A is equal to P inverse B into P, where I'll get this B, matrix B will have same eigenvalues as matrix A. Eigenvalues will be same. And then P inverse is formed using the eigenvectors of matrix A. That's what we have seen already in the similar matrix concept, the similar invariance. Now, based on this, which of the following is not true? Okay. Trace of A equal to trace of B. Since the eigenvalues of both matrix are same, then the trace will be same, determinant will be same. Okay. Eigenvectors of A and B are the same. See, eigenvectors need not be same. Even if my eigenvalues are same, but the eigenvectors need not be same for both the matrix. Okay, so once I form this B matrix can have different eigenvectors, but they will have the only same eigenvalues. So this is not true. Then rank of A equal to rank of B. What rank means? Rank is determined by number of linearly independent columns, that means, or rows, that means number of distinct eigenvalues. So that means both will have same eigenvalues, therefore they will have same number of independent rows or linear combinations. Therefore rank will always be equal. Next, eigenvectors corresponding to distinct eigenvalues of a square matrix are. Eigenvectors correspond to distinct eigenvalues of a square matrix. Distinct eigenvalues means, previously I told, they are always linearly independent. That is the nothing but the number of independent rows is nothing but the rank of the matrix. That's what how you solved in row echelon forms. Next, let A be a 2 cross 2 matrix with eigenvalues 2, 3. Which of the following are correct? Straightforward question. So product of the matrix is, eigenvalues is the determinant. Trace is sum. So what is the eigenvalue of a cube? Eigenvalues will be 2 cube and 3 cube, 8 and 20. So this is also correct. A is invertible because lambda is not equal to 0. Eigenvalues are not equal to 0. So it is invertible. So all of them are next. If A is an upper triangular matrix, then its eigenvalues are of A are. So eigenvalues are nothing but the diagonal elements of upper triangular matrix. If A is diagonalizable with A equal to P into D into P inverse, then which of the following are true? Okay. A is diagonalizable, that means A equal to P into D into P inverse. D will have the same eigenvalues as A, and then P will be formed using the eigenvectors of A. Now, eigenvalues of A power k are the kth powers of eigenvalues of A. Okay, this is true. This is straightforward property. Any matrix, their eigenvalues will give you the power of k. So A square means lambda square. That's how you solve. Then eigenvectors of AK are the same as A. Okay. The eigenvectors are coming from the same matrix. Okay. So see, don't get confused with D and A. They are asking not D. In the previous example you saw A is equal to P into B into P inverse. So this matrix and this matrix are different. Okay, this matrix and this matrix are different. That's why you said B and A may not have the same eigenvectors. Okay. Here they are saying eigenvectors of A power k are the same as A. So we are not talking with B here or D here. We are talking if A has some eigenvectors, say V1, V2, the A power k, say for example A square, will also have the same eigenvectors. That is the meaning. Because how you write? You write it as A into V is equal to lambda V. That means what? If I write A k into V is equal to, I will write it as lambda k. That is eigenvalue will be to the power k into V. So only thing is you will write it as, say if it was 2 and vector is say 0, 1, 1. Here it will be 4 into vector will remain same. Only it is the scaling factor. So vectors will remain same. That is the meaning. Next. Determinant of A power k equal to determinant of AK. So that means what? Determinant of AK is, determinant of AK can be written as lambda 1 power k into lambda 2 power k, so on. Okay. So this is nothing but equal to what? You can together write like this. So this is nothing but what? Determinant of A, right? Whole power k. So that statement holds. Now trace of A power k is equal to trace of AK. So how will you write determinant of, sorry, trace of A power k is equal to sum of all the eigenvalues. Okay, power k. This is not equal to writing same like n1 plus n2 plus so on power k, because this is not a proper mathematical property. You cannot write it like this. That means what? 1 plus 2 plus 1 square 2 square, okay, is equal to writing 1 plus 2 square. This is wrong, right? This will be 5, this will be 9. So this is not correct. If A is invertible, which of the following is always true? If A is invertible means eigenvalue will never be 0. 0 is an eigenvalue of A. No. 0 is not an eigenvalue of A inverse. Eigenvalues of A are negative. You cannot say anything. Eigenvectors of A inverse are different from A. No. So A inverse and A A and A power k will always have same eigenvectors. Please remember this point. Then A and A transform may not have same eigenvectors. May not have same eigenvectors. So this is the properties. Let A be 3 cross 3 matrix with eigenvalues 2, 3, 5. Then which of the statements are correct? Determinant is product 2 into 3 into 5. Trace of A is equal to sum of all the elements 10. Eigenvalues of A transform are 2, 3, 5. So eigenvalues of A transform will always be remain same. This is also correct. Eigenvectors of A and A transform are always same. No, they may not be same. Okay. Next. If A is the eigenvalues, lambda 1 equal to 1, lambda 2 equal to minus 1, then eigenvalues of A square are. A square is lambda square. That is 1 square and minus 1 square. That is both equal to 1 only. So this. Which of the following statements are true for any square matrix? Trace of A is equal to sum of eigenvalues. Determinant is product of eigenvalues. Eigenvalues of A transform are equal to eigenvalues of A. Yes, this is true. But vectors, no. Okay. So eigenvalues of both will be same, but eigenvectors will not be same. If A has an eigenvalue lambda equal to 0, then A is not invertible because determinant will become 0. Rank cannot be n because if it is not invertible square matrix, then that means what? It cannot have n. If it is determinant is not equal to 0, okay, then I can say the rank is n, and if it is invertible. Let A be a 2 cross 2 matrix. Which of the following statements are always true? So this already you know. Eigenvectors corresponding to distinct eigenvalues are linearly independent. Eigenvectors corresponding to distinct eigenvalues are linearly independent. Yes, because what is that you apply A into V is equal to lambda V. If these lambda values are distinct, I'll get this distinct vector. That is the meaning. Then rank of A is equal to 2. So how can you find this? The rank of A can be 2 only if you assume lambda 1 and lambda 2 are not equal to 0, but they haven't mentioned anything. So if lambda 1 or lambda 2 is equal to 0, then rank will be less than 2. It cannot be 2, right? Because it is not invertible. So this is not correct. If a 3 cross 3 matrix has eigenvalues 0, 2, 3, then rank of A is equal to. Okay, so now you'll see. So if you observe here, there is an lambda equal to 0, eigenvalue is 0. That means this is not invertible. If the matrix is not invertible, then the rank will be less than n. So n here is 3. Rank of this matrix will be definitely less than 3. That is using the properties of ranks. Then, so this is ruled out. Now, what about 192? Now, what exactly rank says? Rank is number of linearly independent column. So, there are three distinct eigenvalues. Three distinct eigenvalues will give me three linearly independent rows. But one of them is lambda equal to 0. So that means what? One I will get as 0 vector, which is not an eigenvector. That's what I told you before. So that means what? I have only two linearly independent rows. Therefore, rank will be 2. Okay. Next. Let A be a 3 cross 3 matrix with distinct eigenvalues. Distinct eigenvalues they are saying. Which of the following are correct? Okay. So distinct means lambda 1, lambda 2, lambda 3, 3 values, and they are not equal. Distinct. Now A is diagonalizable. We'll come to this later. First we'll see A inverse exists. So if for A inverse to exist, lambda 1, 2 or 3, any one of them should not be 0. If any one of them is 0, then I cannot find the so this is not true because they haven't given the any values for lambda 1, lambda 2, lambda 3. Because the reason here is distinct they are saying, but they are not saying 0. Distinct can be 0, 1, 2 also. They are distinct, but it's 0. This is not true. Similarly, rank cannot be 3. If lambda equal to 0, rank will be less than 3. Now, eigenvectors corresponding to distinct eigenvalues are linearly independent. What it means? See, if I have distinct lambda 1, lambda 2, lambda 3, I will have distinct vectors. Right? Even for 0, I will get a vector. Okay, it need not be always 0 vector. We'll see one example, you'll understand. So this can be true. A is diagonalizable. So if you have distinct vectors, linearly independent vectors, then A is definitely diagonalizable. That is the meaning. It is all depends on how many linear vectors you form. Okay. So diagonalization means what? This has to hold. A is equal to P into P inverse. So how will you get this P? D is a diagonal matrix. D, you write it here. P into D into P inverse. Now P is the matrix, diagonal matrix, formed from say lambda 1 like this. Only the eigen values for the matrix. This is D. How will you form P? P is nothing but, so 3 columns are there, means 3 vectors V1, V2, V3. So that means what? For this example, I need 3 vectors to form this matrix into P inverse of this. So that is all distinct eigenvalues, then definitely I will get 3 distinct linearly independent vectors. Then eigenvalues of I power n plus a are, you already know, lambda I plus 1. Next, let A be invertible. Which statements are true? Eigenvalues of A inverse are reciprocals of eigenvalues of A because A is invertible. Determinant of A inverse equal to 1 by determinant of A. This is also true because what they are saying is this is 1 by lambda is the determinant of, if the determinant of A is lambda, then 1 by lambda is the determinant of A inverse. That is true. Similarly, trace. Okay. What it means is determinant of A is equal to lambda 1 into lambda 2 into lambda 3, for example, say for this matrix. Now, this will be of what will be determinant of A inverse? If I write it as by determinant of A, this will be 1 by lambda 1 into lambda 2 into lambda 3. So, this is the statement, this is true. Then, eigenvalues of first one, A inverse are reciprocals of eigenvalues of A, that is true. Okay, because lambda is the eigenvalue, then it will become 1 by lambda, that is the property. Now come to trace. Trace of A inverse equal to 1 by trace of A. So trace of, let us say, A equal to lambda 1 plus lambda 2 plus lambda 3. So this may not be equal to 1 by lambda 1 plus lambda 2 plus lambda 3. So this is not true always. Now 0 is not an eigenvalue of A inverse. That's so, because it's invertible, so lambda cannot be 0. Next, if A is diagonal with diagonal entries 2, 3, 4, then eigenvalues of A square plus 2i are. So A square plus 2i means 2 square plus 2, okay, then 3 square plus 2 4 square plus 2. So 6, 11 and 18 false. Next. Determine whether the matrix, given matrix, is diagonalizable. If yes, find a diagonalizing matrix P and diagonal matrix D such that this condition holds. How will you find a matrix is diagonalizable if you can find n independent eigenvectors? So let us find the eigenvectors for this. 4 minus lambda 1 0 4 minus lambda equal to 0. So 4 minus lambda square is equal to 0. So lambda equal to 4. With only one eigenvalue. That means what? That implies I will get only one eigenvector, say V1. But I need to form this matrix P. It will be equal to V1, V2. This is the matrix. V2 is not there because there is only one eigenvalue. So this is not diagonalizable. Let A be a 3 cross 3 matrix with eigenvalues 1, 1, 2. Then which of the following statements are true? See, here we observe that two eigenvalues are 1. That means all the eigenvalues are not distinct. If all the eigenvalues, when I say all the eigenvalues, for example, 3 cross 3 matrix, there will be 3 eigenvalues, lambda 1, lambda 2, lambda 3. All will be distinct, then can definitely say A is diagonalizable. But here, all 3 eigenvalues are not distinct. Lambda 1 equal to lambda 2 equal to 1, they are given. That means what? This A may be diagonalizable or may not be. We don't know. We need to check and find the eigenvectors for these. So next we'll see one similar example where even if they are not distinct, then also we may get A to be diagonalizable. So this is not always true. Not always. Maybe or may not be. When they say all eigenvalues, that means they are saying the total eigenvalues possible for that matrix. So all are included. And then if they say distinct, all will be distinct. Or if they say not distinct, so then you have to check. So they are all are distinct, then definitely it is diagonalizable. If they are all are not distinct, then it may or may not be diagonalizable. You have to find the eigenvectors for it. So trace of A is equal to product of eigenvalues. This is sum of eigenvalues, that is true. Determinant is product of eigenvalues, true. Next, eigenvectors corresponding to repeated eigenvalue are linearly independent. This may not be true. Repeated eigenvalue, for example, say how you apply matrix A into V equal to lambda V. Now lambda, let us assume it as 1, and then I'll get vector 1 as C, say 0, 1, 1. If I take another vector V2 for same lambda value, if I get it as say 0, 2, 2. Eigenvectors corresponding to repeated eigenvalue are linearly independent. No. See, here it is just a scale version of this same matrix. V1, can write it as 2V2. Okay, 2V1 equal to V2. That means what? They are not linearly independent. Next, diagonalize this matrix. So first you have to check whether it is diagonalizable or not. And then if it is diagonalizable, then find the diagonalize. We have to diagonalize this matrix. So first find all the eigenvalues. So this will be 3 minus lambda 0, 0, 0, 2 minus lambda 1, 0, 1, 2 minus lambda. So determinant of this should be equal to 0. This is 3 minus lambda into 2 minus lambda square minus 1 equal to 0. So we'll get, just say lambda is as 3 equal to 3. Then here 2 minus lambda square equal to 1 implies lambda 1 equal to 1. Then another lambda 2 equal to 3. right? So now if you observe here, all the eigenvalues, 3 eigenvalues are possible for this 3 cross 3 matrix, and all of them are not unique. All of them are not unique. That means 3 3 is repeated. So we just cannot say that it is not diagonalizable. Let us check if we can find 3 independent vectors. Let us take lambda 1 equal to 1. For this, we will find the eigenvectors. So what this will become? This will be 3 minus lambda, that is 2, 0, 0, 0, 1, 1, 0, 1, 2 into the vector x1, x2, x3. This should be equal to 0. This will become 2x1 equal to 0, x1 equal to 0. Then x2 plus x3, here it should be 1, is equal to 0. So last, this also becomes x2 plus x3 equal to 0, that is x2 equal to minus x3. Let we'll put x3 equal to t. Okay. Then I will get x2 equal to minus t. x1 is already fixed, x1 equal to 0. Okay. So what will be the vector? Let's say this is as v1. So this will be t into 0, minus 1, 1. This is one vector. Also, see, you can also take x2 equal to t, then x3 will be minus 1. So that will be 0, 1, minus 1. That also you can find out. Okay. v1, let us check only this one vector. Then we will take lambda 3 equal to 3 or lambda 2 equal to 3. Both are same. Now, what will be this matrix? It will be 0, 0, 0, 0, minus 1, 1, 0, 1, minus 1 into my vector. Will be equal to 0. Now, minus x2 plus x3 equal to 0. Take both of these, it is nothing but x2 is equal to x3. Let us say x3 is equal to t. Therefore, x2 will also be equal to t. So now x1 is a free variable because it's not fixed anywhere. So x1 I can take it as, take both 1 into t, or I can take it as 0 into t. Now, when let us say x1 equal to 1t, then what will be my vector? Say v2 is equal to t into 1, 1, 1. Now v3 is equal to, if I take 0, what it will be? It will be t into 0, 1, 1. Okay, here, for example, if I take the other way, let us say v4 equal to t into 0, 1, minus 1. This is also possible. Here, all these are independent, linearly independent vectors. None of them are repeating here, right? So that means what? I have sufficient eigenvectors. I have sufficient eigenvectors. Even if the eigenvalues are repeated, I am getting sufficient eigenvectors. How many I have to get? If P is, what is that I want to find? PD, P inverse for diagonalization. This should be equal to A. Then P is nothing but column vectors V1, V2, V3 into D is diagonal matrix. So all diagonal entries will be the eigenvalues. That is nothing but 1, 0, 0, 0, 3, 0, then 0, 0, 3. This is my diagonal matrix. Then you find the P inverse. So for this, so we need at least, we need 3 vectors, eigenvectors. So I could find more than 3 eigenvectors. So for any given eigenvalues, or for any given matrix, just remember this, there can be any number of eigenvectors. Okay, it's not that always it's equal to the size of the matrix. So there can be any number of eigenvectors linearly independent. That means all distinct. So that is the concept of it. So what is that you have found here? Even if all the eigenvalues are not distinct, but still I am able to find the 3 independent eigenvectors. So this matrix is diagonalizable. So this is the diagonal form. If you want, you can just put this, find the values and then verify. So P will be Let us take any of these three eigenvectors 0, minus 1, 1, 0, 1, minus 1, 1, 1, 1. Okay, into D into P inverse you find. So it will be equal to A. That's the property. I hope you are getting it. So key thing to remember here is, even if the eigenvalues are not distinct, it may or may not be diagonalizable. That's what you have seen in the last question. Next, check whether this matrix is diagonalizable. First, find the eigenvalues. 2 minus lambda 1, 0, 0, 2 minus lambda 1, 0, 0, 2 minus lambda. This is 2 minus lambda into 2 minus lambda square minus 0 equal to 0. 2 minus lambda whole cube equal to 0. Lambda equal to 2. Now, there is only one eigenvalue possible for this matrix. So, we have to check whether it is diagonalizable or not. So, there should be at least 3 values, okay, eigenvalues, but only one I am getting. But let us check anyhow. So, when lambda is equal to 2, let us find our vectors. So, this will be 0, 1, 0, 0, 0, 1, 0, 0, 0 into applied over my matrix x1, x2, sorry, vector x1, x2, x3. So this will be x2 is equal to 0, 3 equal to 0, x1 is a free variable. So it can take 1 into t or 0 into t. Now what will be vector 1? If I take 1 into t, this will be 1, 0, 0. So this is a valid vector. But I need how many? 3 vectors minimum. v1, v2, v3. Why? Because my p is equal to column vectors v1, v2, v3. I could find only one now. So with 0, can I find another one? So if take v2 equal to t into becomes 0, 0, 0. I told you before, this is not a valid eigenvector 0, 0. So what can find only one eigenvector. Thus, this is not diagonalizable. Not diagonalizable. Okay. So in my book, I have summarized all these properties in example with examples. Anyhow, I also carried out the video lectures here. Please go through it carefully in the exam. Please read the questions carefully. Thank you for watching. Please like, subscribe and share.